Are inverses, and you guys have learned about this before. I'm not sure if you remember what that word is, but could somebody give me an example of operations that are inverses of each other? Adding and subtracting. Okay, what are some more inverses that you've worked with before? Yeah. Multiplication and division. And then there was one that you learned in Math 3 that you might not remember. One starts with an E and the other starts with an L. Log and exponential, yeah. So exponents and logarithms. Yeah. Yeah, so squares and square roots. Yep. So when we think about inverses really are just operations that undo each other. They're operations that undo each other. So that's what all of these things have in common. These are operations that undo each other. Okay, so one thing that you know that you've never put words to is that the additive identity is 0. If you were to take any number and add 0 to it, you get the original number. 5 plus 0 is 5. 3 plus 0 is 3. -7 plus 0 is -7. So you can take any number, and if you add the additive identity to it, it's not going to change the number at all. It's going to keep the number the same. Does that make sense? Okay, so we're going to say 0 is the additive identity, and that's because anything plus 0 is itself. That's what it means to be the additive identity. Anything plus 0 is itself. Now, the other part of the additive identity is that if you do two inverses, if you were to do 5 take away 5, addition and subtraction, a positive number and a negative number, if you were to do those two things together, what does it equal? It equals 0, which is the additive identity. So if you were to take two inverses and put them together, it gives you that additive identity when you're doing those two operations together. Does that make sense? Okay. What is the multiplicative identity? 1. It's 1. Anything times 1 is itself. Anything times 1 is itself. And the same thing is true if you were to multiply a number by the inverse of the number, you would get 1. So, and you can think of, with multiplication, you can think about multiplying by the inverse of the number, which would be like the fraction. I could take 3 and multiply by 1/3, right? That would be like multiplying by the inverse. Or I could think of division. I could do 3 divided by 3. And that would also be like an inverse operation. Do you guys see how that would work? So I could say 3 times 1/3 gives me that multiplicative identity, or I could say 3 divided by 3 equals 1. That gives me that multiplicative identity. So we've never called them that before, but we've used them. We know what they are. We've seen them before. Okay, so we're going to use that same idea, but we're going to look at it with matrices today. So we're going to look at the multiplicative identity matrix, specifically for a 2x2 matrix and for a 3x3 matrix. And one thing that we're going to kind of highlight, if you have a highlighter or if you have, if you just have a pencil, you can put a star next to it. Identity matrices, so we're going to look at the identity, they're always square matrices, which means it's going to be a 2x2 or a 3x3. And this is what they look like. 1, 0, 0, 1. Now if I do a 3x3, it's going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, now we're going to come back to this part right here, and you guys are going to tell me why they have to be squares. We don't know it yet, but you're going to come back later and you're going to tell me why they have to be square matrices, why it couldn't be a 2x3, why it couldn't be a 1x4, why it couldn't be a 5x1, because there's a very reasonable explanation about why they have to be a 2x2 or a 3x3 or a 4x4. There's a very reasonable explanation. Okay, so first example says multiply matrix A by its identity matrix. We're just going to see what happens. So I'm going to write down kind of some shorthand notation so you guys can see what some shorthand for matrices looks like, because nobody wants to have to write down the matrix every time. So I'm going to say A multiplied by its identity, and I want to see what that's going to equal. So here's the notation down here. And then over here, I'm just going to do the actual work. So here's matrix A. Since this is a 2x2 matrix, I'm going to multiply it by 1, 0, 0, 1. And if I have a 2x2 multiplied by a 2x2, then I can see that the 2 in the middle match, and I'm going to get a 2x2 as an answer. So I already know my answer is going to look like this. Okay, so if you guys remember, when we multiply matrices, our left finger goes across the row, our right finger goes down the column. So for the first spot, we're going to do 2 times 1. What do we get for that? 2. And then negative 7 times 0. 0. So I get 2 plus 0 is just 2. Okay? For this spot right here, I'm going to stick with the first row, but I'm going to do the second column. So I'm going to get 2 times 0, 0, and then negative 7 times 1. Negative 7. Okay? Now this is the second row, but the first column. So I'm going to start with the second row, start with the first column. I've got 5 times 1 and 6 times 0. So 5 and 0 is 5. And then here I've got the second row, second column. So I've got 5 times 0 and 6 times 1. All right, so when I multiply those, what do I get? I get A. So if I do A multiplied by the identity, I get A. So this is the exact same thing as if we were to do a regular multiplicative identity. We're used to that. Anything multiplied by 1 gives you itself. A matrix multiplied by the identity is kind of like multiplying by 1. It's just a matrix that kind of represents 1. Yeah?
Is that why it's like set up with the zeros in there?
Mm-hmm. It's set up with the zeros in there, yeah. So, and it's the same thing. It's any square matrix where you have 1s on the diagonal, and they have to be this specific diagonal. They have to go that direction, and then zeros everywhere else. That's what would make it work. Okay, so now let's go ahead and try the next problem. So here we're going to talk about how inverses and the identity matrix, how those work together. So for this example, it wants us to multiply A times B and then multiply B times A. So if you guys remember, when we were multiplying matrices together, the order mattered. if you switched the order of the matrix, you could either get a different answer when you switch the order, or if you switch the order, it would mean you couldn't even multiply them at all. The dimensions might not be accurate so that you could actually even multiply them to begin with. So here, let's multiply a times b to start with. So I'll put the a first, and then the b. And I have a 2 by 2 times a 2 by 2, so I know that a 2 by 2 is going to be my answer. Okay, so if we start multiplying these, our first number is going to be in the first row, first column. So we have 1 times negative 2 and 2 times 3 halves. 3. So negative 2 and 3 is 1. Okay? Then we have the first row, second column is 1 times 1 and 2 times negative 1 half. Negative 1. So 1 and negative 1 is 0. Okay. Now we're in the second row, first column. So 3 times negative 2, negative 6. And then we have 4 times 3 halves, 6. So negative 6 and 6 is 0. Okay. And then second row, second column. 3 times 1, 4 times negative 1 half, negative 2. 3 and negative 2, 1. So what just happened is we did A multiplied by B, and we got the identity matrix. Okay? Now let's do B multiplied by A and see what we get. So negative 2 times 3 halves, 1, negative 1 half. 1, 2, 3, 4. Okay. All right, so we're in the first row, first column. So negative 2 times 1, negative 2, 1 times 3, 3. So negative 2 and 3 is 1. Negative 2 times 2, negative 4. 1 times 4, 0. Okay. 3 halves times 1, 3 halves. Negative 1 half times 3, negative 3 halves. So 3 halves and negative 3 halves, 0. Okay. And then 3 halves times 2, 3. Negative 1 half times 4, negative 2. So that's 1. And so then over here we got B times A equals the identity. Okay, so if we go back up here, if you have two things multiplied together that equal the identity, that means that those two things were inverses. Okay, so A times B equals the identity, B times A equals the identity. If this happens in matrices, if they both equal the identity, and when you go both directions, that means that A and B are inverses of each other. So this answers the question, why does the identity matrix have to be a square? And the reason is because you have to be able to switch the order. You have to be able to say this 2 by 2, this 2 by 2. So here we had these two dimensions matching and these being the leftovers. But here when we switch them, 2 by 2 and 2 by 2, when we switch them, it's different dimensions that are matching up. So here these are the interior two that are matching up. over here, those are the exterior two. And the interior two are different ones that are matching up. Does that make sense? So that's why your identity matrix has to be a square. There's no other option. So this makes something interesting because we're actually used to, if you were doing addition and subtraction, I could give you any number and I could say, I've added 5, undo that operation. And you could say, okay, minus 5. I've added 10, undo that operation. Okay, minus 10. I've subtracted 7, undo that operation. Okay, I'll add 7. Or I could say, all right, I've multiplied by 3, undo that operation. And you'd say, okay, divide by 3. With matrices, we can't do that. If I multiplied something by a 2 by 3 matrix, and I want to undo that operation, I cannot possibly undo that operation because there is no inverse for a 2 by 3 matrix. Once you multiply by a 2 by 3, you're done. That matrix is there. That operation is forever. Does that make sense? So if you multiply by a 2 by 2, you can undo that. If you multiply by a 4 by 4, you can undo that. But as soon as you multiply by a 1 by 4, that's going to stick forever. Does that make sense? Okay, so that's kind of the interesting thing about matrices. All right, let's turn the page. Okay, so they're going to have us do it again just to prove that these are AB and BA are going to give us the identity. So we're going to try AB first. And this is a 3 by 3. So 1, negative 2, negative 1, 0, 1, 1, 2, 1, 2. And when you look at two matrices, there isn't, the way to find a matrix is not so obvious that you could just glance at them and go like, oh yeah, those are inverses. You really would have to multiply them out and do the math to be able to tell that they're inverses or not. So it's not as simple as positive 5, negative 5, oh, those are inverse, additive inverses of each other. Or 3, 1/3, those are multiplicative inverses of each other. They're not as obvious as the more simple operations. Okay, so if we do A times B, we have a 3 by 3 and a 3 by 3, which means the identity is going to be a 3 by 3 when we multiply the two inverses together. So if I'm doing this upper corner right here, that's going to be the first row and the first column. So my left finger is going to go across the row. My right finger is going to go down the column. So I've got 1 times negative 1, and then 0, and then 2. So what do I have? I got 1. Negative 1, 0, and 2 gives me 1. Okay, so now I've got first row, second column. I've got negative 2, 0, 2. Negative 2, 0, 2. What does that give me? 0. Okay, now I'm on the first row, third column, so I've got 2, 0, negative 2. 0. Okay. So now I'm on the second column, or second row, first column. So I've got 2, negative 3, 1. 2, negative 3, and 1. 0. Okay. Second row, second column, I've got 4, negative 4, 1. 1. Okay. I've got negative 4, 5, negative 1, 0. Third row, first column, I've got 1, negative 3, 2, 0. 2, negative 4, 2, 0. And then negative 2, 5, negative 2, 1. Whew. That hurts my brain. Okay, so we have A times B equals 1. All right, I want you guys to take a moment and I want you to verify that B times A equals the same thing. So take a moment, multiply B times A, and let's make sure that B times A gives you the exact same thing. So if A times B is the identity and B times A is the identity, then matrix A and matrix B must be inverses. That's how we prove it. And it has to go both ways. You have to prove it in each direction. I don't know if it's possible for you to have a situation where A times B is the identity and B times A is not. I'm guessing it's possible because this is a thing, but I would have to search for an example to show you. I'd have to search for one. That would be an interesting thing to Google to see if you could find one that's not true. Okay. So the next question is, now that we know that inverses are a thing with matrices, that they have to be square, it has to be a 2x2, it has to be a 3x3, it has to be a 4x4. The next question is, like, how do you find the inverse? In this class, we're only going to find a 2x2 inverse because 3x3 gets a lot more difficult, and it's only in upper level math, like beyond pre-calc, beyond high school math, that they start to use those inverses. Typically, when you're in high school level math, they'll use a calculator for the 3x3s. So first, we have to find something called a determinant. And the determinant, if you look down here for the inverse, it helps you find the coefficient that you then multiply the inverse by. So first, we're going to look at finding the determinant, and then we'll find the actual inverse. So if you have matrix A and we say that it's just like A, B, C, D, the determinant is if you take the A and the D and you multiply them together first, and then you subtract off B times C. So the way that I remember which one to do first is I remember that we live in America, and well, we speak English, and when most English-speaking countries, all of them, not most, all of them, read from left to right, and we read from top to bottom. So the first one that you multiply is from left to right, top to bottom, A to D. Does that make sense? That's the one we do first, and that's how I remember. So if we were to find the determinant for the first example, we would do 3 times 5. Left to right, top to bottom. Does that make sense? That's the one we do first. So 3 times 5 is 15, and then we're going to subtract off the other one. -1 times 2 is -2. So the determinant there is 15 minus -2 is 17. It's not hard to find, it can just be tricky to remember. So the next one, the determinant, we read left to right, top to bottom. -3 times 3 is -9 minus the other one. -6. -9 minus -6 is -3. Okay. And then last, 2 times 5 is 10 minus -3 is 13. Okay. So that's how you'd find the determinant. Again, not difficult, just got to remember it. Okay. The same thing is true with finding the inverse. It's not difficult to find, you just have to remember it. Okay. So if the determinant does not equal 0, then the inverse of matrix A, known as A inverse, you've seen this notation before. So if you remember back when you were finding inverses in Math 3, when you found inverses in Math 3 of equations, you would trade the x and the y coordinate of an equation, and then you would solve for y. Do you guys remember doing that back in Math 3? Trade x and y, solve for y? Well, the notation for inverse is just to put like an exponent of -1 there, but you don't say a to the -1. You don't read it like an exponent. You read it as A inverse. So let's put this above. We're going to say A inverse. This is how you read it out loud if you were to say it. A inverse. That's how you read it. So you do 1 divided by the determinant, and you use this as a coefficient. So you're going to take this number, whatever it is, and you're going to multiply it by each of the numbers inside of the matrix. Okay? Now, if your matrix for A is A, B, C, D, all those numbers, then you can see that the A and the D have switched places. Everyone see that? The A and the D have switched places. And the B and the C have switched signs. Not difficult, you just have to remember it. So the A and the D have switched places, the B and the C have switched signs. Does that make sense? Okay, so one thing we have to remember is that the determinant cannot equal 0. Why would it make sense that the determinant cannot equal 0? Yeah, not 0. It would be 1 divided by 0 is, try it on your calculator real quick. Somebody do 1 divided by 0 on their calculator. One divided by 0 is error. It's undefined. Your calculator doesn't divide by 0. Nobody divides by 0. It's undefined. So as long as your determinant is not 0, you can find the inverse. So now we have 2 things we have to look out for. We have to have a square matrix, and our determinant cannot be 0. Does that make sense? So as long as those 2 things are happening, then we can find the inverse. So we're going to look for our determinant. We're going to make sure it's actually a number, that it's not 0. And then we can do 1 over determinant, and we're going to switch the places of the A and the D, and we're going to switch the signs of the B and the C. Hardest part of that is just remembering it. So I took this first example. We already found the determinant. I brought it down here. So I'm going to switch the placement of the 3 and the 5. So 5 up here, 3 down here. And then I'm going to switch the signs of the -1 and the 2. So it's going to be a +1 and a -2. Now my determinant was 17, so I'm going to put a 1/17 in the front. And now I just have to take my 1/17 and multiply it by each of those numbers inside the matrix. So you'll notice that unless the person writing the problem has been very deliberate to make sure that the inverse does not have fractions, it is very common for your inverses to have fractions in them, okay? So my inverse here is going to be 5/17, -2/17, 1/17, 3/17. And it's ugly, but that's the inverse. All right, let's go ahead and turn the page. So for this one, we're going to switch positions for A and D. So +3 up here, -3 down here. And then for the B and C, we're just going to switch the signs. And then I'm going to go back to where I found the determinant on the previous page. -3, 6, -1, 3. This one, the determinant was -3. So I'm going to do 1 over -3. I'll put the negative out in the front. So 1 over -3 in the front. So -1/3 times 3 is -1. -1/3 times 1 is -1/3. -1/3 times -6 is 2. -1/3 times -3 is 1. There's my inverse. All right, and then this last one, switch the order of the 2 and the 5. Switch the signs. So +1, -3. Take my discriminant, which was 13. I'm going to put a 1/13 in the front. So we've got 5/13, -3/13, 1/13, 2/13. All right. How do we feel about finding the inverse? Okay, so what's the purpose? We didn't talk about this a lot, but what's the purpose, do you think, of finding an inverse? If we go back to regular math, go back to the first page of the notes, adding and subtracting, what's the purpose of knowing how to do both of those? If you do it, you can undo it when you're solving an equation, right? What's the purpose of knowing multiplication and division? If you do it, you can undo it. What's the purpose in Math 3 of learning about exponents and logarithms together? If you do it, you can undo it. What's the purpose of learning about squares and square roots? If you can do it, you can undo it. So today we're learning about inverses of matrices. So what's the purpose of knowing the inverses of matrices? We want to be able to undo it, okay? So tomorrow we're going to learn about, yes, I know how to multiply matrices, but when would I want to undo a matrix? That's why we're learning about it today. Because tomorrow we're going to want to undo a matrix and we're going to see how it's going to help us solve something. Does that make sense? Okay, so for today, the thing that is difficult, the thing that we want to remember, and it's not difficult mathematically, it's just difficult memory-wise. We want to remember how to find the determinant, and we want to remember the little trick for how to find the inverse by hand. Make sense? Okay, so